Welcome to Table Management lesson. Today we continue our journey through PostgreSQL object management capabilities, covering the exact same structure we saw 2 lessons behind when our focus were how to create tables in their columns constraints. In our previous lesson, we explored how to manage container objects, altering databases, schemas, and tablespaces. We learned about operations like renaming, changing ownership, and modifying various properties of these container objects. Today we will apply similar concepts to tables, specifically focusing on table structure management, how to rename tables, change ownership, modify tablespace, and how to drop them safely or forcefully. Column structure management, how to add, rename, and drop columns, as well as change the data types with all related implications. Finishing with managing extra attributes. This topic is actually so big that we'll leave all constraint management to the next lesson, despite being technically part of table management. Let's start the table structure management with one of the simplest operations, renaming a table. The syntax for renaming a table in PostgreSQL is clean and intuitive. Start with the command alter table, current table name, then rename to new table name. For instance, if we have a table called customer data and want to rename it to just customers, it's as simple as that. This command is executed quickly as it only updates the system catalogs. It doesn't need to rewrite the actual table data. There are some caveats though, as other objects might be impacted. When you rename a table, PostgreSQL automatically updates most dependent objects to reference the new name. However, there are important exceptions. Views, stored procedures, and functions that reference the table by name in their SQL code will not automatically be updated. These will continue to reference the old table name and will generate errors when executed. None of them will be covered right now in this section, so it should be fine. Nonetheless, it's important to identify all dependencies before renaming tables in a production environment. Tables in PostgreSQL have owners, and sometimes you need to transfer ownership from one role to another. The command is similar to previous objects we've seen, alter table owner to. For example, to transfer ownership of the customers table to the role named sales team, just do alter table customers owner to sales team. It's important to highlight some permission considerations. To change the owner of a table, you must be the current owner of the table or a super user, have the ability to set role to the new owner. The new owner must have create privileges on the table's schema. This ensures that ownership transfers maintain proper security boundaries. If any of these conditions aren't met, the operation will fail with a permission error. Ownership changes are particularly important in multi-team environments, where different groups are responsible for different parts of the database schema. To move a table to a different tablespace, run alter table. In this example, customers, set tablespace. Let's use a possible tablespace called fast SSD. There are performance implications to consider, especially for large tables. When you change a tablespace, PostgreSQL physically moves all tables' data files to the new location. For large tables, this operation can take a significant amount of time, require sufficient disk space in both locations during the move. Block other operations on the table while the move is in progress. For large tables, let's say tens of hundreds of gigabytes, consider performing these operations during maintenance windows when the system is under minimal load to avoid major disruptions. Once you finish with a table or need to remove its part of schema changes, PostgreSQL provides a drop table command to permanently remove tables from your database. The basic syntax for dropping a table cannot be easier. Drop table, table name. For example, to remove a table called old customers, you just do drop table old customers. This command permanently deletes the table and all its data. Be careful as this cannot be reverted. Postgres also supports dropping multiple tables in a single command, and you just need to separate them with commas, like in this example. When dropping a table that other objects depend on, like views, foreign keys, or triggers, PostgreSQL provides 2 options to handle these dependencies. Drop table, in this case products, restrict, which is a default behavior. Alternatively, you can type drop table cascade. The restrict option prevents you from dropping a table that has dependencies. This serves as a safety mechanism to avoid unintended consequences. The cascade options, on the other hand, automatically removes all objects that depend on the table being dropped. And this includes views that reference the table, foreign key constraints in all the tables that reference this table, triggers attached to the table, and rules defined on the table. I know there's plenty of other objects that we haven't covered yet, but let's focus for now on the most popular ones. Dropping a table is generally a fast operation, but there are some performance aspects to consider. One is transaction isolation. Drop table acquires an exclusive lock on the table, blocking other operations until the transaction completes. For large tables in busy systems, this can impact concurrent operations. Second, system catalog updates. PostgreSQL needs to update various system catalogs when dropping a table. While this is typically quick, it can take longer in database with many objects. Third, storage reclamation. When you drop a table, PostgreSQL marks the disk space as available for use, but doesn't immediately return to the operating system. The space becomes available for new PostgreSQL objects. Remember that dropping a table is irreversible once the transaction is committed. Always ensure you have proper backups before dropping tables in production environments. Now that we've covered these basic table-level operations, let's dive into column operations, which are among the most common schema modifications you'll perform. So let's explore each type in detail. All column operations are under alter table command. Consequently, they are all prefixed by alter table, table name, then the column operation, which can be add, rename, alter, or drop. For all of them, the keyword column can follow the column operation name, and we will use it in all of our examples, but this is optional. To add new column, the column operation is add or add column. Then you specify a column like you did on the create table command. The difference is you can only add one column at a time. And because of that, there is no parameters surrounding the whole column definition. In our example, just type email voucher 255. It's still like we did when created tables. We can also add columns with column level constraints. For example, alter table customers, add column status, voucher 20 default active, to define a column that will be populated with active when records are inserted without providing explicit values. Another example is not null. So again, alter table, customers, add column, created at, timestamp, not null, default, current timestamp. This time we added both, not null and default. Well, it's fine when we insert values without providing explicit created at timestamps, or setting them as default. However, it's when we specify null that an error occurs. And that's because null is being explicitly enforced, but the column has not null constraint. And I'm bringing on these two examples because when adding columns to existing tables, PostgreSQL employs different strategies depending on the column's default value and null constraint. So let's explore these scenarios in detail. First, adding a column without default and without not null, in other words, allowing nulls. It's an instantaneous operation as PostgreSQL only needs to modify the table's metadata. No table scan or data rewrite is required. Second, adding a column with a non-volatile default. It's optimized by Postgres by storing the default value in the system catalogs, rather than writing it to every existing row. As we saw in the table creation lesson, this approach is storage efficient because it avoids repeating the same data from each row. Now we are also highlighting this as performance efficient, as especially in large tables, this smart mechanism avoids full table rewrites. Third, adding a column with volatile default. It's an operation that requires a full table rewrite anyway, because PostgreSQL must evaluate the volatile expression for each existing row to store the result. This of course can be time-consuming for large tables. In this example, the created at values of all existing rows will be the timestamp when the alter table was executed, which produces an interesting scenario where a DDL command produces value like DML commands. Adding a not null column without default. It runs fine only if the existing table is completely empty, but it fails if the table contains at least one row of data, as PostgreSQL won't be able to determine the value for that field. This verification is necessary to maintain data integrity. Fifth, adding a not null column with a non-volatile default combines the efficiency of scenario tool with skipping not null checks. And that's because PostgreSQL doesn't need to scan the table as the default value ensures no nulls will exist. Last but not least, adding a not null column with a volatile default. It's similar to scenario 3 and requires a full table rewrite to evaluate the volatile expression for each row. The not null constraint, on the other hand, is implicitly satisfied by the default values, unless they return null. The verification process for not-null constraints without default is crucial for maintaining data integrity. If PostgreSQL didn't perform this check, it could lead to inconsistent data states where existing rows contain null values in a not-null column. When adding columns, consider the trade-offs between immediate operation completion, allowing nulls or using non-volatile default, and data integrity guarantees, using not-null constraints. For large table operations, requiring full table rewrites can be significantly time-consuming and may impact database performance. Understanding these behaviors allows you to make informed decisions when modifying table structures, especially in production environments where minimizing downtime is crucial. Okay, done with not-null and default. So now columns with generated values can also be added, like alter table customers add column full name text generated always as, and then your formula stored. Adding a store-generated column to an existing table in Postgres requires a full table rewrite because Postgres needs to calculate and physically store the generated values for all existing rows. This operation can be time-consuming for large tables, similar to adding a column with a volatile default value. With virtual columns, the alter table operation will be nearly instantaneous since it will only need to update metadata in the system catalogs, without rewriting the table data. This will be similar to how Postgres handles adding a column with a non-volatile default value. Let's now deal with existing columns. So the first and obvious example is renaming columns. I'm pretty sure you can guess what the command is. Pause the video and think about it. Okay, so introducing the command alter table customers, rename column contact number to phone. If you pay attention, the syntax is very close to renaming the table itself. As the column keyword is optional, what actually makes sure we are renaming a column, not a table, is the current column name we write after rename. As you saw previously, alter table, table name, rename to new name, renames the table. It's when we inject a current column name between rename and to that we are renaming the column. Similar to renaming tables, renaming columns can impact dependent objects like views, functions, triggers, and stored procedures, as they will continue to reference the old column name and may generate errors when executed. So it's always advisable to check for dependencies first. Moving on to change columns data types. The command is a bit odd, and let's call it alter table alter column type, because type is also a mandatory part of the command. And again, column is optional. Type is mandatory because it tells the exact type of alteration we are applying to the column. So to change a column type, you type something like alter table customers, alter column notes, type text. As you can imagine, changing column types might lead to compatibility issues, as PostgreSQL attempts to convert existing data to the new type. When old and new types are compatible, like varchar to text, integer to big int, conversion generally succeeds without issues. However, when conversions may result in data loss, such as numeric to integer when decimal places are truncated, larger types to smaller types of varchar, for example varchar 100 to varchar 50, timestamp with time zone to timestamp without time zone, where time zone information is lost. Existing data is also a concern. When data matches the new type, the conversion happens seamlessly to the new type. However, when data doesn't match the new type, there are two possible outcomes. If the conversion is possible but lossy, PostgreSQL performs the conversion with potential data loss. If the conversion is impossible, for example, converting ABC to an integer, the alter command fails with an error. For example, when converting a text column containing 1, 2, 3 and ABC to an integer, an error like this is thrown. Column status cannot be cast automatically to type integer. And that makes sense. You need to change or delete this data first. In Postgres utility belt, there is another great tool to help us with type conversions. It's the using clause. This clause provides explicit control over the conversion process. You use it by appending using in an expression to your alter table, alter column type command. In this example, we did nothing special as double column integer is just a simple explicit cast to integer, which is already what Postgres would do anyway. But this is particularly valuable for 1. Complex conversions, when the default casting rules are insufficient, like this call to a function toDate. That allows us to specify the date format. Imagine order date as being a varchar, but all existing data follows this format of 4 numbers for a year, dash, 2 for month, dash, 2 for day of month. 2. Conditional conversions are also possible. For example, handling different data formats with the same column. So let's evolve our example to accept multiple data formats in our previous varchar column. We are still going to cover functions like toDate and case statements, so don't worry with them for now. The goal is just to understand that with case, Postgres checks each value to be converted if they match certain regular expression. If yes, then convert using toDate function that use the same format. And 3. Default values for incompatible data. Providing fallbacks for data that can't be converted. This way we just added an else clause to cater for all badly formatted data stored in our varchar column, to be null as they don't fall into any recognizable data format. This saves the entire operation from failing because of this ugly data. Other aspect to ponder is performance, as changing a column's data type typically requires a full table rewrite, which can be very time-consuming for large tables. Bear in mind that during this operation, the entire table is locked against writes. Sufficient disk space is needed for the rewritten table. All indexes on the table must be rebuilt. Tables with gigs of bytes, hundreds of millions of rows, a type change can take hours to complete. In such case, instead of directly altering the column type, consider alternative approaches like: Step 1. Add a new column with the desired type. Step 2. Copy data in batches to reduce log time. We will cover the DML command, so don't worry for now. Step 3. Drop the old column. Step 4. Rename the new column to the original name. Now that we've discussed important aspects of altering columns, let's talk about dropping them. To remove a column from a table, run alter table, table name, drop column, column is optional again, column name. Like this example, who in the world still uses schemas? If other objects depend on the column you are dropping, you can use the cascade option, as the cascade option automatically drops any object that depend on the dropped column, such as constraints, indexes, and views that reference the column. Of course, this can have a far-reaching effects, so use it with caution. When you drop a column, differently from dropping a table, PostgreSQL doesn't immediately reclaim the physical storage space. The rows still occupy the same amount of disk space, but the dropped column is marked as unavailable. The space is only reclaimed when the table is eventually rewritten by a vacuum full, cluster, or certain alter table operations. For large tables, this means dropping columns is a quick operation. It only updates the system catalogs, but it doesn't immediately free up disk space. If reclaiming space is important, you need to follow up with a vacuum command, but leave it for now. When working with existing tables, you often need to modify column attributes beyond just adding, renaming, or changing data types. PostgreSQL provides several alter table, alter column operations to let you manage column level constraints, default values, and generated expressions. To manage column level constraints, PostgreSQL allows you to set, modify, or remove column level constraints after table creation. To set or drop a not null constraint to or from an existing column, you simply type alter table products, alter column description, set not null, or alter table products, alter column description, drop not null. While drop not null is super fast because there is nothing to check, set not null operation scans the entire table to verify that no rows contain null values in the specified column. If any null value is found, the operation will fail with the same error as when we add a new not null column to populated table. This can be avoided using not valid instruction, but we'll discuss this in a bit. You can also add or modify column's default value. Again, the command is very simple. Alter table customers, alter column status, set default, say active, a non-volatile value. Or alter table orders, alter column order date, set default current timestamp, a volatile value. To remove a default value, no dramas, alter table products, alter column, in stock, drop default. These operations only affect future insert operations and don't modify existing data. Similar to dropping not null constraints, they are metadata only changes that execute quickly regardless of table size. Let's now see how to manage generated expressions. Even though generated values can be stored, the only implemented option in 2 PostgreSQL 18 arrives, which means each row is written with its own value. Converting non-generated columns into generated is currently also not supported. Different from the command alter table add column generated that we saw before, a command to only set generated, similar to set default or set not null, to existing columns produces a syntax error. So unfortunately, if you type alter table products, alter column full price, set generated always as your formula and store, you get a syntax error like that. However, if the column has originally been added as generated, a set expression as action can be used to update the generation expression. Like this one, assuming that full price was added with a generated expression. Alter table products, alter column full price, set expression as, and say price times 1 plus tax rate. This syntax also limits you from changing from generated always as to generated by default as or vice versa. Finally, to confirm you cannot make a regular column a generated column, the same set expression command will fail if the column wasn't generated. But because you are running a syntactically valid command, it doesn't raise a syntax error, but a more precise error message saying, hey, this column is not a generated column, so sorry. You can go in the opposite direction though. To convert a generated column back to a regular column, there is a simple command, alter table products, alter column full price, drop expression, and yes, you type the keyword expression, not your actual expression. I've seen people doing that. After this operation, the column becomes a regular column containing the previously generated values. Bear in mind that it can no longer be converted back to a generated column like we discussed before. To work around this, you can drop and add the column again, but you might need extra steps depending on whether your generated column is always or by default. If the intention is to convert a regular column to generated always column, there is not much to be concerned about because the new column will store or compute according to your new expression. However, generated by default suggests that rows can store values different from the expression's result. So you might want to keep existing row values. For that, first, add a new generated column with a different name, like in this command where we add a full price to column, generated by default as our expression. Second step, update existing records, copying values from old regular column to the new generated column, where they are different from the new expression results. We'll still cover the update command in this section, so don't worry for now. Step 3, drop the old regular column as you have migrated the data that you need. Step 4, to finish the operation, rename the new generated column to the old column's name. In step 5, just before you go, remember to reclaim disk space as like we've seen on drop column action, PostgreSQL doesn't free up space automatically when columns, not tables, are dropped. We'll cover vacuum command in section 6, performance and optimization. Wow, this lesson was intense. Despite being only 2 sections, table structure and column management, there's quite a lot you can, and yeah, a few you cannot do to fully manage your tables. Next, we'll continue with more constraint management on tables, and jump into sequences, keys, and indexes. See you!